cost to install 115-volt outlets in a new steel building using electrical metallic tubing or EMT conduit will vary depending on several factors. Firstly, location influences costs. The cost of materials and labor can vary significantly depending on the location of the building and the accessibility of the electrical system. Secondly, the number of outlets impacts the overall price. The more outlets that are needed, the higher the cost will be. Thirdly, the complexity of the installation affects the estimate. If the outlets are located in hard-to-reach areas or require special wiring, the cost of installation will increase. Fourthly, materials play a role in the total price. The type of EMT conduit and fittings used can also affect the cost. Based on these factors, here is a general breakdown of what you can expect to pay for 115-volt outlets in a new steel building using EMT conduit. Materials may cost approximately $5 to $10 per outlet. Labor may cost approximately $10 to $20 per outlet. Therefore, an expected cost is $15 to $30 per outlet for the materials and labor to install a 115-volt outlet in a new steel building using EMT conduit. In addition to the materials and labor costs, there are several other factors that can affect the total cost of the installation, such as permits and inspections. Depending on your location, you may need to obtain permits and have the electrical system inspected. Disposal of old materials also has to be factored. If existing outlets are being replaced, the cost of disposing of the old materials needs to be considered. Warranty is another consideration, as some electricians offer warranties on their work, which can provide peace of mind. It is important to get quotes from several electricians before making a decision. This will help ensure that the best possible price is being obtained for the installation. When planning electrical installations, several key considerations are crucial for ensuring safety, efficiency, and compliance with regulations. Firstly, understanding local electrical codes is paramount. These codes, often based on the National Electrical Code, or NEC, specify the standards for wiring, grounding, and safety devices. Compliance with these codes is not only a legal requirement but also essential for preventing electrical hazards such as fires and shocks. Secondly, proper circuit planning is vital. This involves determining the appropriate number of circuits needed to handle the anticipated electrical load. Overloading circuits can lead to overheating and potential fires, so it's important to distribute the load evenly across multiple circuits. The NEC provides guidelines for calculating circuit loads and determining the appropriate wire gauge for each circuit. Thirdly, grounding is a critical safety measure. A grounding system provides a path for fault current to flow back to the source, tripping a circuit breaker or fuse and preventing electrical shock. The grounding system must be properly installed and connected to all metallic components of the electrical system, including conduit, enclosures, and equipment. Fourthly, selecting the right wiring method is essential. EMT conduit is a common choice for commercial and industrial applications due to its durability and ease of installation. However, other wiring methods such as rigid metal conduit, or RMC, or flexible metal conduit, or FMC, may be more appropriate for certain situations. The choice of wiring method should be based on the specific requirements of the installation, including the environment, the type of building construction, and the applicable electrical codes. Fifthly, using quality materials is crucial for ensuring the long-term reliability and safety of the electrical system. Cheap or substandard materials can fail prematurely, leading to electrical hazards and costly repairs. It's important to use materials that are listed and labeled by a recognized testing laboratory, such as Underwriters Laboratories, or all, to ensure that they meet industry standards for safety and performance. Sixthly, proper installation techniques are essential for ensuring the integrity of the electrical system. This includes using the correct tools and methods for cutting, bending, and joining conduit, as well as for terminating wires and making connections. Improperly installed wiring can lead to loose connections, overheating, and electrical hazards. Seventhly, testing and inspection are critical steps in the installation process. Before energizing the electrical system, it should be thoroughly tested to ensure that all wiring is properly connected and that all safety devices are functioning correctly. A qualified electrical inspector should also inspect the installation to verify compliance with applicable codes and standards. Understanding how to calculate voltage drop is crucial for ensuring the efficient and safe operation of electrical circuits, particularly in long runs of wiring. Voltage drop refers to the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction, reduce the brightness of lights, and increase energy consumption. Firstly, the formula for calculating voltage drop is voltage drop equals current times resistance, or volts drop equals amps times ohms. This formula can be used to calculate the voltage drop in a single conductor. However, for AC circuits, a more complex formula is often used to account for the effects of reactance and power factor. Secondly, factors that affect voltage drop include the length of the conductor. The longer the conductor, the greater the voltage drop. This is because the resistance of the conductor increases with its length. The current flowing through the conductor. The higher the current, the greater the voltage drop. This is because the voltage drop is directly proportional to the current. The size of the conductor. The larger the conductor, the lower the voltage drop. This is because the resistance of the conductor decreases with its cross-sectional area. The material of the conductor. Different materials have different resistivities. Copper has a lower resistivity than aluminum, so it will have a lower voltage drop for the same size conductor. The temperature of the conductor. The resistance of a conductor increases with temperature, so the voltage drop will also increase. Thirdly, acceptable voltage drop limits are typically specified in electrical codes and standards. The NEC recommends that the voltage drop in branch circuits should not exceed 3% and that the voltage drop in feeders should not exceed 5%. These limits are intended to ensure that equipment operates properly and that energy is not wasted. Fourthly, steps to minimize voltage drop include using larger conductors. Increasing the size of the conductor will reduce its resistance and lower the voltage drop. Shortening the length of the conductor. Reducing the length of the conductor will decrease its resistance and lower the voltage drop. Using conductors with low resistivity. Copper conductors have lower resistivity than aluminum conductors, so they will have a lower voltage drop. Reducing the current flowing through the conductor. Reducing the current will decrease the voltage drop. Using voltage drop compensation devices. These devices can be used to boost the voltage at the end of a long run of wiring. Understanding the ampacity of conductors is crucial for ensuring the safe and reliable operation of electrical circuits. Ampacity refers to the maximum amount of current, in amps, that a conductor can carry continuously without exceeding its temperature rating. Exceeding the ampacity of a conductor can lead to overheating, insulation damage, and potentially electrical fires. Firstly, the NEC provides detailed tables, such as Table 310.15, outlining the ampacity of various conductors based on their size, insulation type, and installation conditions. These tables are essential for selecting the appropriate conductor size for a given application. Secondly, factors that affect ampacity include the size of the conductor. The larger the conductor, the higher the ampacity. This is because a larger conductor has a lower resistance and can dissipate heat more effectively. The insulation type of the conductor. Different insulation materials have different temperature ratings. Conductors with high temperature ratings can carry more current without overheating. The ambient temperature. The higher the ambient temperature, the lower the ampacity of the conductor. This is because the conductor will dissipate heat less effectively in a warmer environment. The number of conductors in a raceway or cable. When multiple conductors are installed in the same raceway or cable, they can heat each other up, reducing their ampacity. The NEC provides adjustment factors to account for this effect. The method of installation. The way a conductor is installed can affect its ability to dissipate heat. For example, conductors installed in free air will have a higher ampacity than conductors installed in conduit or cable trays. Thirdly, 13 factors are applied to the ampacity of conductors to account for various factors that can reduce their ability to dissipate heat. These factors include high ambient temperatures, multiple conductors in a raceway, and the presence of thermal insulation. The NEC provides tables of deterring factors that must be applied to the ampacity of conductors in these situations. Fourthly, selecting the appropriate conductor size involves considering the ampacity of the conductor, the load it will be carrying, and any applicable deterring factors. The conductor must be sized so that its ampacity is equal to or greater than the load it will be carrying after applying any necessary deterring factors. Fifthly, overcurrent protection devices, such as circuit breakers and fuses, are used to protect conductors from overloads and short circuits. These devices are designed to trip and interrupt the flow of current if the current exceeds the ampacity of the conductor. The overcurrent protection device must be sized so that it will protect the conductor without nuisance tripping. Understanding grounding and bonding is fundamental to electrical safety. Grounding provides a path for fault current to flow back to the source, tripping a circuit breaker or fuse and preventing electrical shock. Bonding ensures that all metallic components of the electrical system are electrically connected, creating a low impedance path for fault current. Firstly, grounding systems typically consist of a grounding electrode, such as a ground rod or a metal water pipe, connected to the neutral conductor at the service entrance. The grounding electrode provides a connection to the earth, which helps to stabilize the voltage of the electrical system and provides a path for fault current. Secondly, bonding is the process of connecting all metallic components of the electrical system together, including conduit, enclosures, and equipment. This creates a low impedance path for fault current, which helps to ensure that the overcurrent protection devices will trip quickly in the event of a fault. Thirdly, the NEC specifies detailed requirements for grounding and bonding, including the size and type of grounding conductors, the methods for connecting grounding electrodes, and the requirements for bonding different types of equipment. Compliance with these requirements is essential for ensuring the safety of the electrical system. Fourthly, equipment grounding conductors, or EGs, are used to connect the metallic enclosures of electrical equipment to the grounding system. These conductors provide a path for fault current to flow back to the source, tripping a circuit breaker or fuse and preventing electrical shock. Fifthly, bonding jumpers are used to connect different sections of metal conduit or other metallic raceways. These jumpers ensure that the entire raceway system is electrically continuous and provides a low impedance path for fault current. Sixthly, ground fault circuit interrupters, or GFCIs, are used to protect people from electrical shock. These devices monitor the current flowing in a circuit and will trip if they detect a difference of 5 mA or more between the hot and neutral conductors. GFCIs are typically required in wet locations such as bathrooms, kitchens, and outdoor areas. Seventhly, arc fault circuit interrupters, or FSIs, are used to protect against electrical fires. These devices monitor the current flowing in a circuit and will trip if they detect an arc, which is a dangerous electrical discharge that can ignite flammable materials. FSIs are typically required in bedrooms and other areas where people sleep. Understanding overcurrent protection is essential for preventing electrical fires and protecting equipment from damage. Overcurrent protection devices, such as circuit breakers and fuses, are designed to trip and interrupt the flow of current if the current exceeds the ampacity of the conductor or the rating of the equipment. Firstly, circuit breakers are resettable overcurrent protection devices that use a bimetallic strip or a magnetic field to trip and interrupt the flow of current. Circuit breakers are available in a variety of sizes and types, including standard thermal magnetic breakers, ground fault circuit interrupters, or GFCIs, and arc fault circuit interrupters, or FSIs. Secondly, fuses are one-time use overcurrent protection devices that use a fusible link to trip and interrupt the flow of current. Fuses are available in a variety of sizes and types, including standard plug fuses, cartridge fuses, and time delay fuses. Thirdly, the NEC specifies detailed requirements for overcurrent protection, including the size and type of overcurrent protection devices, the location of overcurrent protection devices, and the requirements for protecting different types of equipment. Compliance with these requirements is essential for ensuring the safety of the electrical system. Fourthly, the interrupting rating of an overcurrent protection device is the maximum amount of current that the device can safely interrupt. The interrupting rating must be high enough to handle the maximum fault current that could occur at the point of installation. Fifthly, selective coordination is the process of coordinating the overcurrent protection devices in an electrical system so that the device closest to the fault will trip first, minimizing the disruption to the rest of the system. Selective coordination is important for ensuring the reliability of the electrical system and for preventing unnecessary outages. Sixthly, short-circuit current rating, or SCCR, is the maximum short-circuit current that a component or assembly can withstand without failure. The SCCR of a component or assembly must be equal to or greater than the available fault current at the point of installation. Understanding electrical wiring methods is essential for ensuring the safe and reliable installation of electrical systems. Various wiring methods are available, each with its own advantages and disadvantages. Firstly, electrical metallic tubing, or EMT, is a thin-walled steel conduit that is commonly used for indoor wiring in commercial and industrial buildings. EMT is easy to install and provides good protection for conductors. Secondly, rigid metal conduit, or RMC, is a thick-walled steel conduit that is used for outdoor wiring and for wiring in hazardous locations. RMC provides excellent protection for conductors and is resistant to corrosion. Thirdly, intermediate metal conduit, or IMC, is a medium-walled steel conduit that is used for both indoor and outdoor wiring. IMC provides a good balance of protection and cost. Fourthly, flexible metal conduit, or FMC, is a flexible conduit that is used for connecting equipment to the electrical system and for wiring in tight spaces. FMC is easy to install but does not provide as much protection for conductors as EMT or RMC. Fifthly, non-metallic sheaths cable, or NM cable, is a type of cable that consists of two or more insulated conductors enclosed in a non-metallic jacket. NM cable is commonly used for wiring in residential buildings. Sixthly, armored cable, or AC cable, is a type of cable that consists of two or more insulated conductors enclosed in a flexible metal jacket. AC cable is used for wiring in both residential and commercial buildings. Seventhly, cable trays are used to support and route cables in commercial and industrial buildings. Cable trays are available in a variety of sizes and materials. Eighthly, wireways are enclosed raceways that are used to protect and route conductors in commercial and industrial buildings. Wireways are available in a variety of sizes and materials. When installing electrical systems in steel buildings, it is essential to consider the specific requirements of this type of construction. Steel buildings present unique challenges due to the conductive nature of the steel frame and the potential for corrosion. Firstly, grounding and bonding are critical in steel buildings. The steel frame must be properly grounded to provide a path for fault current and to prevent electrical shock. All metallic components of the electrical system, including conduit, enclosures, and equipment, must be bonded together to create a low impedance path for fault current. Secondly, corrosion protection is essential in steel buildings, especially in damp or corrosive environments. Galvanized steel conduit and fittings should be used to prevent corrosion. Conductors with moisture-resistant insulation should be used. Thirdly, proper support and attachment methods are necessary for securing conduit and cable to the steel frame. Conduit and cable should be supported at regular intervals to prevent sagging and damage. Attachment methods should be chosen that will not damage the steel frame or compromise its structural integrity. Fourthly, fire stopping is important for maintaining the fire resistance of the building. Any openings in the steel frame for conduit or cable should be properly fire stopped to prevent the spread of fire. Fifthly, coordination with other trades is essential for ensuring that the electrical system is properly integrated with the other building systems. The electrical contractor should work closely with the other trades to ensure that the electrical system does not interfere with the mechanical, plumbing, or structural systems.